Welcome to The Explainer. Today we're going to talk about the evolution of parallel programming. It's really the story of how we went from manually juggling all these complex operations to, well, just elegantly describing the work we need done. It's what makes our modern apps so fast and efficient.
So let's just kick things off with a fundamental question. Think about it. An app has to do a bunch of things at once. And sometimes one part of the program has to wait for a bunch of other parts to finish their jobs. So how does it keep track of everything without, causing total chaos? How does it know when everything's actually done? That right there is the core problem of synchronization.
And the answer? Well, it's a journey. It's the story of how developers went from being total micromanagers, having to control every single tiny step of the process, to becoming more like architects. Architects who just lay out the plan, describe the work that needs to get done, and then trust the system to handle all the complicated details for them.
So here's the crucial point. When you've got multiple worker threads chugging away in the background, you absolutely have to have a rock-solid way for the main thread, the boss, if you will, to just wait for signals from all of them at the same time. If you don't have that, you've got a recipe for disaster.
Early on, developers basically had two main tools for this job. On one hand, you had this really powerful function that was specific to Windows, and it could listen for a bunch of different signals all at once. Pretty handy. But on the other hand, you had a more universal, cross-platform solution called condition variables. But it required a completely different way of thinking, a whole different pattern.
Now, what's really fascinating here is just how different the approach was between these two. It all boils down to when you lock the data you need to work on. With the Windows method, you'd wait for a signal to come in, and then you'd lock the data to safely read it. But with condition variables, you actually did the reverse. You'd lock the data first, and then when you told it to wait, it would cleverly unlock it for you, and then automatically relock it when the signal finally arrived. It's a subtle difference, but it has huge implications for how you write your code.
In fact, this whole cross-platform pattern was so counterintuitive for developers who were used to the Windows way of doing things that, well, it was often seen as a total mystery. All of this confusion and complexity was basically a giant blinking sign for the whole industry that said, hey, we desperately need a simpler, better way to handle all this.
And that complexity, that was the catalyst. It kicked off a major turning point, a real paradigm shift in how people thought about parallel programming. It was time to get away from the low-level, nitty-gritty details of threads and move into the much more abstract world of tasks.
For the longest time, everything was about threads. So what's a thread? Well, it's a very low-level, direct command you give to the computer's operating system. It's kind of like giving a team member a super detailed step-by-step checklist. You're telling them exactly how to do the job. You're managing the how.
A task, on the other hand, that's a whole different ballgame. It's a much higher-level concept. A task just represents a piece of work that needs to be done. You're not giving out that step-by-step checklist anymore. Instead, you're just giving your team member a goal, and you're trusting them to figure out the best way to get it done. You're defining the what.
And this slide just nails that mental shift perfectly. We went from focusing on the how, all that manual low-level plumbing of creating and managing and synchronizing threads, to focusing on the what. Just defining the jobs we need to get done and letting a smart library handle all that messy worker management for us. It was a real game changer.
But as you can probably guess, this powerful new world of tasks, well, it came with its own very specific, very common, and, let's be honest, very confusing trap that a lot of developers fell into.
Okay, let me walk you through this because it's a classic. Imagine you write a simple for loop to create 20 tasks, one for each number from 1 to 20. Simple enough, right? Wrong. Here's the hidden problem. The task doesn't actually grab the value of the number at that moment. Instead, it grabs a reference, a pointer, to the loop variable itself. So what happens? By the time those tasks actually get around to running, the loop has already finished, and that variable is now sitting at its final value, 21. So all 20 of your tasks wake up, look at the variable, and think they're supposed to process the number 21. And the fix, which is the crazy part, is so simple. You just pass that variable to another function. That one simple action forces the compiler to capture the value right then and there, not the reference. Problem solved. All right, so once we finally mastered this shift to tasks and we've learned how to sidestep those common pitfalls, there's one final, even higher level of thinking that makes all of this parallel programming stuff more powerful and more declarative than ever.
And this brings us to the world of parallel patterns. Just think of patterns as pre-built, optimized solutions for common problems.
So instead of manually creating a bunch of tasks for a loop, you just use a parallel for pattern, and bam, the library automatically figures out the best way to split that work across all your computer's cores. Need to get a result from a background job that's not done yet? You use a pattern called a future. It's like using high-level building blocks instead of trying to make everything out of individual bricks.
So, the big takeaway here is this. The whole evolution from threads to tasks and finally to patterns isn't just about getting a few new features. It's a fundamental change in how we're supposed to think about writing concurrent code. It lets us write code that's cleaner, waste-saver, and a whole lot faster. And that leaves us with a final question to chew on. As our computers keep getting more and more cores, are you still thinking down in the weeds with threads, or are you ready to think in patterns?